my name is Anthony DeDios, and this is my project of chaos theory for Rita Than's Math 207. An intro to chaos theory is that it's essentially the study of random and unpredictable behavior in a system that isn't determined by an external system having fixed conditions with expected outcome, like you would in like a science experiment where you have your hypothesis and then you end up getting the results that you believe or are more than likely think are going to happen. In chaos, a system moving from stable points to unstable points, which is explained simply as randomness, is what chaos theory is. You never know what's going to happen in the system. You can have the exact same starting values and everything in your system and have different results every time, which is why it's called a chaotic system. Some general applications for chaos theory are predicting the trajectory of stars, predicting weather systems, typically like hurricanes or tornadoes that are going to be happening in areas, but overall just the weather. As you can see in my picture, double pendulums. So essentially, those are chaotic systems because you never know what's going to happen based on the initial conditions from where it was released or how hard it was pushed. It will always be random and chaotic because of having the double pendulum. So you never know where it's going to move. And then you have the famous butterfly effect. Um, that is a chaotic system because you have two different fixed critical points, and the way that the system works is that they will never connect or touch, but they will always loop around both those critical points, and that is a great way of figuring out like weather patterns or mixing solutions for chemistry, since you won't necessarily know where things are going to be moving, but they will always intertwine between both those critical points. The Lorentz system is a three-dimensional autonomous differential equation, and the way that it's broken up is a very simple system where dx over dt is equal to sigma times y minus x, dy over dt is equal to x times rho minus zeta, and then minus y, and then dz over dt is equal to x times y minus beta times zeta. And then those three parameters are beta, sigma, and rho are all proportional to the Prandtl and Rayleigh number. And for those variables, x, y, and z are x is the rate of convection, y is the horizontal temperature difference, and then z is your vertical temperature gradient, which is why this system specifically is very good for predicting weather and thermal and fluid changes. Lorentz, the professor from MIT who found this system, found that chaos can only happen when the parameters for sigma is equal to 10 and then beta is equal to 8 over 3. And generally, chaos starts to happen when rho is equal to about 24. And then after a long period of time of changing rho, it will eventually become a fixed system instead of a chaotic system. In order for us to begin using the Lorentz system, we essentially take our three equations and then we're going to put them into a Jacobian and then make it into a 3 by 3 linear matrix function. And then for this, I'm going to be substituting mu in for y2. So that way now we have the 3 by 3 matrix, and J is going to end up being singular. So after this, we can now use those, the equation where mu is equal to plus or minus the square root of beta times rho minus 1, in order to find our critical points that we will see inside of our Lorentz attractor after we get these values. As you can see, the Lorentz attractor is essentially based off of rho. So since we know that beta and sigma are constants that Lorentz found, the only contributing factor to the chaos is rho. So as you can see, when rho is 10, you don't really see anything crazy. It's just kind of like sine waves going. And then right around when rho is equal to 24, we begin to see that chaos is happening. Uh, Around 25 to 30 seconds, we can start seeing that the systems are starting to act different. Um, and then at rho equals 30, now we have differences between each one of our values, x, y, and z. And we can see now that their behavior has now changed and they're no longer similar. So jumping rho values from 24 to 30 tends to show our system being chaotic, and then it'll tell you around what time it's going to begin to change using the Lorenz attractor, which is this method right here. For my example, I picked a weather prediction example. So I used to suggest the pattern of the likelihood of a hurricane in Florida. We were told that the rate of convection is at 7, the horizontal temperature difference in Florida is 6.9, and the temperature gradient of 11.3, and rho with a value of 28. With this information, can you please model the critical point and the Lorenz attractor? So since we know that our constants, sigma and beta, are fixed, and it's 10 and 8 over 3, the derivation of this equation is now simplified down to just solving our 3 by 3 matrix and then using the formula for critical points, and then plugging in the information to get our critical points. So we know that based on just our information, our critical points are going to be 29, 8.485, and then negative 4.85. And then based on all that information and then plugging in our values, I'm able to use MATLAB and a system in MATLAB to graph the Lorenz attractor. And as you can see, around the values of 8, after about 8 seconds, that's when the point of chaos begins to happen in our system. And then in the other form of the Lorenz attractor, because the Lorenz attractor on the left before you get the butterfly wings, that is the same as the butterfly wings on the right, only it's broken up into um, just X, Y, and Z. So those are the movements and changes of X, Y, and Z. Only now we're able to put it into a picture. And after 10 seconds, there's not a whole lot of chaos happening, but you can see that based on our critical points, it's jumping from our 3 critical points, which would be in the middle, and then the 2 giant holes that are we are circling around. And as 20 seconds goes by, you can see that there's a lot more frequency on the left than there is on the right. And then after 50 seconds, you can now clearly see the way that the butterfly wings are taking shape, and they're still circling around both those critical points, which is why this is a great way to predict the weather as you're going about using the Lorenz system. To conclude, the chaos theory in general is very helpful for the future since it's a great way to model and predict things, specifically space, weather, economics, and more recently, pandemic crisis management. And although there is a lot of issues with predicting uncertainty and how a slight variation will change, if we're able to get a better method for handling chaos, then we will be able to do better for humankind in general in the future on predicting things that could be dangerous, like a hurricane, tornadoes, economic crises. So overall, I do believe that chaos theory is very beneficial, and I hope that one day we're able to find a better system to predict all these uh, unknowns in the future. That is my presentation, and I hope you guys enjoyed. Thank you.